Hello, everyone. Welcome to the webinar, Friction is Not Friction, Optimizing Conveyor Drive Performance. I'm Dr. Tarun Srivastava, Technical Sales Manager at Elastotec. I'm here with my colleagues from Elastotec, Brad Lawson from Conveyor Dynamics, and the presenter of the webinar, Dr. Peter Robinson from the University of Newcastle. Today's webinar is based on the ongoing research work to identify the accurate value of coefficient of friction between the conveyor belt and different types of pulley lagging. It is a part of a joint research project between Elastotec, the University of Newcastle, and Conveyor Dynamics. This joint research project has been initiated after a catastrophic pulley lagging failure in a gold mine in Australia. Where conveyor had to stop for 3 days due to this lagging failure. The production loss which happened due to this lagging failure was more than $20 million. After this failure, Elastotec collaborated with Conveyor Dynamics and the University of Newcastle to identify the root cause of this failure. And we did detailed engineering analysis. And as a result of detailed engineering analysis, of this failure, we realized that this analysis can be very useful to identify the most suitable lagging for each conveyor application. So based on this engineering analysis, a tool called Lagging Select has been developed. Lagging Select utilizes the variant friction model to obtain the coefficient of friction between the belt and the lagging. The University of Newcastle is basically helping us to improve the lagging select variant friction model by performing friction experiments and identifying the accurate value of coefficient of friction around the arc of contact and under different operating conditions. So this webinar will describe the research work on friction. The presenter of the webinar, Dr. Peter Robinson, is a research associate at the University of Newcastle and has also held a consulting position at Tundra Bulk Solids. Peter is an expert in optimizing material handling systems with a particular focus on belt conveying. His interest in this field arises from his deep commitment to addressing the existing research gap and overcoming the challenges in the field. As such, Dr. Robinson's extensive knowledge and experience makes him an ideal candidate to guide us through the complexities of the belt conveyor systems. Peter's presentation will take approximately 20 to 25 minutes. Please feel free to put any of your questions you may have in the chat box, and there will be time to discuss these questions after the presentation. My colleague Mariana will facilitate the questions, and Peter and Brad will respond to them. So now I would like to hand over this to Peter.
That's it, going up.
Perfect, thank you.
Thanks, Peter.
Now, hopefully this comes through. Has that come through, Taryn?
Yes.
Perfect, thank you. So as Taryn introduced me, I'm a research engineer with the University of Newcastle. Many of you would be familiar with either us or Tundra Bulk Solids. We work very closely hand in hand, looking at materials handling systems and the material themselves, I suppose. My background is in belt conveying. For the last 12, 13 years, I've been looking at design and optimization of complex conveyor systems, mostly pipe conveyors and pouch conveyors, but friction and drive performance has been a key focus over the last 3 or 4 years. So the presentation today is to give a bit of an overview as to what we know and what we still don't know in terms of friction and drive performance. Hopefully it'll certainly raise some questions, and hopefully it'll answer a few as well. But if you do have any questions, just feel free to put them in the chat and I can get to them at the end. All right, so as Taryn suggested, this is some work that has been collaboratively performed between ourselves, Elastotec obviously, and Conveyor Dynamics in the US. We're kind of staging a multi-pronged approach to try and solve this issue from different fronts. We're looking at the definition of friction between the belt and the pulley surface, whether it's lagged or bare steel. Elastotec and conveyor dynamics are taking that further, I suppose, and looking at the design implications for lagging and belts as well. So we'll start off with a bit of an introduction as to why we're doing this work. We'll have a look at what motivated this work to occur and the current design practices. We'll go through some of the research that we've done and the results. And of course, at the end, some of the research that we're still yet to do. All right, so a bit of research motivation, and it should come as no surprise that conveyor systems are getting much more complex. It's just an exponential trend that we've seen over the last 20 years or so. Conveyors are continuously getting longer and faster, and of course we need the materials to be conveyed at higher tonnages. All of this translates into basically a higher drive power being transmitted from the pulley to the belt cover. So, of course, the materials themselves are becoming more problematic. They're becoming wetter, stickier, and the ore grade is reducing. All of that essentially leads to handleability issues, losses, contamination between the belt and the pulley as well. So all of this needs to come into play. The big one that Taryn spoke about at the start that kind of fueled this research, or really kicked it in the guts, if you like, is there's a lack of performance and design data to aid selection of lagging and ultimately the design of the drive system. So this was a bit of a glass shattering moment, in that a lot of the lagging selections up until about 2 years ago was done because something worked in some other application. But as conveyors get bigger, higher power, higher tonnages, we're starting to see this selection process start to degrade. We're seeing drives that are upwards of 6 or 8 megawatts through gearless drives now, and it's a hell of a lot of drive power to transmit through a single pulley in a comparatively small contact area with the belt. So we're really starting to demand an improved understanding of the belt and pulley interaction, so that we can optimize the performance of the drive, minimize the stresses on the belt, and of course the lagging as well. All right. So just the point down the bottom, the current design standards, which I'll touch on, there's 3 that most of you are familiar with, I'd imagine, both the DIN, the ISO, and SEMA, obviously. These are the standardized approaches, and all of them take a relatively conservative approach. I'll touch on what this conservative approach is, but ultimately this has the potential to create other issues down the track as well. All right. So the current design methods utilize a formula called the Capstan equation. Now, I'm not here to present equations, so I think this is the only one that I've got. But it is a relatively straightforward equation, just here on the left. Taryn, can you see my pointer? Can you see my mouse by any chance? Yep, perfect, thank you. So this equation on the left basically means that if we've got a belt velocity going to the right up the top, the materials on the top of the belt here, this is what's known as our tight side tension, our F1, wraps around to our slack side tension, our F2. And the Capstan equation basically says that the ratio of these two tensions has to be less than or equal to e to the mu theta. Now, mu is a coefficient of friction between the belt and the pulley, and theta is the angle of wrap. Now, this equation in particular has been around for centuries. It was developed in the mid-1700s, and it was developed for a rope wrapping around a cylinder. So a capstan, of course, is, if there's any sailors in the audience, basically you should have several of these on your yacht. And basically they're normally a fixed or a driven drum with a one-dimensional rope wrapping around it. The purpose of the capstan is to basically provide a mechanical advantage to pulling on a rope. So, of course, this equation has been extended to as many applications as we believe it applies to. So, of course, we use it in conveyor drive design, as we'll go through today. The belt design in your cars, all of the belts were designed using this equation. Rope pulleys, rock climbing, that they all essentially use this one equation. The assumptions of this equation are where it starts to fall over, to be frank. A simple assumption of this equation is that the belt is perfectly flexible. Now, that's a reasonable assumption when it comes to conveyor belts. For the next three, we have seen a limit reached in the application to drive systems. The second one is that the friction is fully developed around the arc of contact. And this is given by a constant coefficient of friction. Basically, this equation is assuming that we are at the point of slip around the entire arc, and that the coefficient of friction around the entire arc is in fact a constant. Now, I'll talk about that in a fair bit of detail today, and I'll present some results to show why it is a limiting factor. The next point is basically tension and face pressures reduced linearly from F1 to F2. Again, it's not a terrible assumption, but we do know that as stick and slip occurs within the arc, it deviates from linearity, and there is more of a constant phase pressure in the stick region. The last assumption is one that I'll talk about in the future work. I won't really touch on it today. And it's the fact that the assumption is that the phase pressure is constant across the width of the contact. Now, here for a new belt, that assumption is probably valid, but as we start to see some wear on either the top or bottom cover, basically the arc length of the carcass of the belt varies across the width, and therefore our phase pressure varies across the width. So that's something that we're looking to look at in a future work, but primarily today I'm going to focus on this second dot point here, the assumption of a constant coefficient of friction that is fully developed around the arc of contact. All right. Now, the way that this design standard overcomes the limitations, I suppose, is that they reduce the value of friction. Okay, so they basically take a conservative approach, but as I said earlier, that does lead to some other complications. All right. Straight out of the design standards, this is straight out of ISO 5048. This standard gives coefficients of friction for 3 different operating conditions, being dry, wet, and contaminated. And we've got 4 different lagging combinations. Now, the fact there's only 4 lagging combinations in this design standard, I suppose, is a bit of a testament to the limited understanding that there is around this topic. There's much more than 4 different types of lagging out there in terms of all different tread patterns, and they all behave differently. But you can see here that for a dry application, which is what I'm going to talk about most today, the coefficient of friction ranges from around the 0.35 to 0.45, depending on the lagging. Okay, if you've got water or contamination, obviously it reduces. But primarily today, I'm going to speak about dry conditions. Yep. All right. Now, the limitation of designing with a conservative coefficient of friction is basically this. If you have a look at the equation on the left, if you understate your coefficient mu here, let's say you're designing for 0.4, but in reality, your coefficient is say 0.8, you overcome this underestimation of your friction by increasing your tension. Okay, so by increasing your tension, obviously you've got an increase in your operating tension. That leads to the selection of a higher rated belt, and obviously your infrastructure and components are overrated as well. Now, all of this essentially leads to higher stresses on the lagging. So it's a bit of a vicious cycle in that you're intentionally designing to prevent slip in your drive system, but you're increasing the stresses on your lagging and increasing the risk of fatigue and failure of that component. So a bit of a double-edged sword. So it certainly is necessary to optimize this as much as we can, and that's the focus of this project. Okay. Bit of an overview of the collaborative research project that we're doing. So we're split it into two sections at the moment, just our component here at the university, and that is basically defining friction and modeling. So primarily today, I'm going to talk about defining friction. We'll talk about multiple lagging products that we've tested. We'll talk about the face pressures and the shear velocities that we've tested at and the impact of both of these. We'll look at some initial work on cover grade and thickness and how that affects friction. And then down the track, we obviously want to test material wear and age properties, temperature and contamination. So those last three are critical to optimum performance down the track instead of on a new belt. Modeling is some work that's being done by one of my PhD students at the moment, and he's looking to develop a finite element model of both the testing that we're doing at the moment and extrapolating that to a full drive system as well. So by modeling the testing that we're doing at the moment, it's basically behaving as a calibration procedure rather. And then once we've calibrated on the testing that we've got, we can extend that to a full drive pulley and optimize the performance as well. All right. I'll talk about a bit of future work towards the end of the presentation. All right. So the research that we've got at the moment, the results that I'm going to present, they've been developed with a friction test facility that we host here at the university in Tundra Bulk Solids. This is a fairly straightforward rig in that this rig takes lagging samples on these inside plates. On both sides of this plate here, you will house a belt sample or a belt cover sample. Then these airbags apply a compressive force between the two. Both of these arms, if you like, are on linear rails and they're self-aligning. So as you compress them, they will self-align around the center of the belt. There's load cells in between the airbags and the frame so that we can track compressive force. And then ultimately, this entire rig is installed in a tensile test machine, which is here on the right. So this is our Shimadzu 5-ton tester. We install it in there. The whole rig weighs about 350, 400 kilos. And once we compress the samples by inflating these pneumatic bellows, we will pull this top crosshead at a varying velocity. Okay, so this crosshead velocity, I call it a few things in this presentation. Primarily, I think I call it the shear velocity. It represents the velocity difference between the carcass of a conveyor and the pulley surface, okay? So in between the pulley surface and the carcass, obviously you have the lagging, and the lagging can deflect, and you have a pulley cover as well, and that can deflect as well. So I'll talk a bit about that. The sample sizes that we test here, they're typically 300 by 300 mil lagging samples in here, and there's obviously two of them. We can apply up to a 12-ton compressive load on this contact, which equates to about 1.3 megapascals of face pressure if we utilize the full lagging size, or we can even go higher if we reduce the lagging size. This Shimadzu can only pull 5-ton, but we do have an option for a 25-ton pull if needed. So far, we've been able to utilize the 5-ton capacity and get all the information that we need. Down the track, we'll test worn and contaminated surfaces. And the slip velocities, we've got quite a lot of freedom in selecting the slip velocity in this rig, but typically you would see a slip velocity up to about 10 millimeters per second between the carcass of the belt and the pulley surface. So they're the results that I'm going to present today. Okay. These results, we've tested 4 lagging samples for this presentation. These are Elastotec products. And we've tested the natural diamond rubber, the direct bond ceramic, the rubber-backed full ceramic, and the polyurethane as well. And we've tested them at different normal pressures, different face pressures and different shear velocities as well. Okay. Now, to give a bit of an overview as to what we see when we run one of these tests, this is each lagging sample, so 4 lagging samples at a given test condition. Now, I've just taken a random test condition just for a comparison. But what we'll see is we basically measure relative to displacement. If I go back here, we basically have up to about 60 millimeters of displacement in this rig before the contact area starts to reduce. Okay, so we can typically analyze up to 60 mil if need be. Okay. You can see here that there is a very different behavior between each of these samples. Okay, if we have a look at the direct bond ceramic, that's the purple line here, the response is quite steep at the start, and it comes up here to a relatively constant coefficient of friction and flattens out. If we have a look at the 80% ceramic, which is the yellow, it has a similar ceramic coverage to the direct bond. It is a slightly shallower response. It's not as steep, and that's because of the rubber backing. And it gets to a slightly higher value in this case, and forms a little peak and then flattens out. In general, we do see a fairly strong alignment between the 80% ceramic and the direct bond. If you have a look at the diamond rubber, which is a natural rubber, it's a shallower profile again. And then if you have a look at polyurethane, polyurethane is quite a complex material to test, and I'll show the results and you'll see this. Basically, the viscoelastic properties of all of these come into play. So what I'm trying to show here is that just the nature of the presentation title is that friction is not friction. The difficulty in defining a coefficient of friction for these lagging samples is real. And it's basically due to the viscoelastic behavior of both the belt and, in the majority of these cases, the lagging samples themselves. Because we've got viscoelastic behavior, we end up with creep or microslip within this contact. Okay. Now, as we start to pull the sample and as we start to create that shear force in the contact, we start to induce creep, and it progresses with an increasing shear force. And you can see it here. Now, if we have a look at the diamond rubber, basically you can see that this coefficient of friction builds up to a constant value after around 30 to 35 mil of displacement. Now, part of that is creep, but also part of that is shear in the lagging in the belt as well. Okay, so at the moment, we're working to define this procedure, but just a few questions to pose here is, the best method to define a coefficient of friction, is it a peak in this plot here? If you have a look at conventional Coulomb mechanics, it differentiates between static and kinetic coefficients of friction, and you would typically see something along these lines, a peak before it comes back down to a constant. Is it at a given displacement, a given rate, where we may take a cut and look at the coefficient of friction at that displacement or that degree of shear, or is it at steady state? Okay, so there's a few different questions to pose. The results that we're presenting here today are at steady state, but normally when we do this testing, we'll present all three cases. Okay. All right, just flicking through a few results. So I've got results for all four lagging samples. This one obviously being the natural rubber, this is the natural diamond. The test that we ran face pressures between 100 and 900 kPa, and they're fairly representative of most applications that you'd see on a head pulley. The shear velocities that we tested again from very, very low of 0.1 up to 10 millimeters per second. The shear velocity is defined by essentially the speed of your belt and the T1 to T2 differential, basically how much it has to contract along the pulley surface, and obviously the elastic modulus of your belt as well. So all of that will define your shear velocity. And you can see here that the coefficient of friction varies with both normal pressure or face pressure and shear velocity as well. Okay, so the ISO standard or the DIN standard basically takes a value of about 0.35 to 0.45 down here. You can see here that our coefficient of friction, again, depending on application, increase well and truly above a 1.0 value as well, so up to about 1.4. So because both the lagging and the belt itself is viscoelastic, we see quite a high dependency on both velocity and normal pressure, and we'll see that change with the ceramic profiles as well. So all of this data is hopefully a little bit simplified over on the right-hand side here as well. So shear velocity down the bottom, pressure on the top, and you can see our coefficient of friction changing with color. If we have a look at direct bond ceramic. Now this is dimpled. You can see that we've got a similar profile with one small change. The magnitude of the range is similar, where 0.4 up to 1.2, but you can see that we've got less dependency on normal pressure now, okay? And that is because we've basically removed half of the viscoelastic material in comparison to the natural rubber. So the direct bond ceramic is, by all accounts, assumed to be rigid. And so the only viscoelastic behavior in this contact is now in the belt cover, okay? So this response is much flatter in terms of pressure, and the primary dependence is in shear velocity as well, okay? But again, all of these values are either at or above the design standards and their coefficient of friction. Okay. Now, if we put a rubber backing on that ceramic profile, again, you'll see that the coefficient of friction range is similar. We're 0.46 to 1.3, whereas previously we were 0.41 to 1.2. And you can see that there is a small increase in the dependency on the pressure. That's because we've got a rubber backing now on the lagging. But ultimately, we do see a similar profile due to the similar coverage and the dimpled nature of both these lagging. Okay. Now, the last one. Now, polyurethane is quite a complex material. We tested it with the same process, and we achieved similar results, but we see a strong non-linearity in both face pressure and shear velocity. Now, we should have some more information on this in about the next 2 to 3 weeks as we start to model the viscoelastic properties of these materials. But at the moment, all we can see is that it is not a consistent trend in either shear velocity or face pressure. You can see here that we do have these dips down here associated with a fairly constant shear velocity, but a change in, a reducing face pressure, whereas historically you would normally see an increase in friction coefficient with reducing face pressure. Okay, so it's a bit of a question at the moment, a question that we're certainly looking to answer, and we should know more in a couple of weeks once we've got some modeling of the viscoelastic properties. Yep. So looking at the belt materials, so we ran some testing to look at the impact of the belt covers. We ran 3 suites of testing. We looked at a 4mm M grade cover, just a general purpose cover, and compared that with an 8mm M grade cover. And then we did the same again for an 8mm low rolling resistance cover as well, okay? Now, we ran that for all 4 lagging types, and we did it at a single velocity just as a benchmarking exercise to try and estimate the difference in performance. Okay? Now, if we have a look at the impact of cover thickness, we tested at a velocity of 2 inches per minute. Now, this does have some basis. There's some literature out there that suggests this is a representative test velocity. And if you have a look, we're comparing the 4mm M grade results with 8mm M grade results, and our 8mm M grade results is the baseline. Okay, so deviation, so each of these columns represents a change that we see in the 4mm M grade results. So you can see, if we have a look at the ceramic samples, first off, if you have a look at purple, which is our direct bond, and yellow, which is our 80% rubber backed, you can see that there is a small amount of change in the results, but it is fairly minimal. It's limited to, say, 5% down here at low pressures. But as you increase the pressures, it makes sense that the deviation reduces. When you have a look at the polyurethane, the deviation increases up to about 8%. And again, it's inconsistent. Just the nature of the polyurethane suggests the nonlinearity with both face pressure and shear velocity. The diamond rubber, which is slightly thicker, I believe, than the polyurethane, it has a stronger dependency as well. So we're seeing that the 4 mil M grade results, or the coefficient of friction for a 4 mil cover, is around 5 to 12% less than it is for an 8 mil M grade cover. Okay, so all of these results aren't consistent. We're not seeing a consistent drop or increase in friction with a reduction in cover thickness. And again, it forms part of our path forward. So it's just another question that we're looking to answer. Okay. If we have a look at a similar plot for different cover grade, again, the results suggest some trends, but also pose some more questions. So this is a comparison between our 8 mil low rolling resistance cover, taking an 8 mil M grade cover as our baseline. Okay. Now, again, start with the ceramic samples, our purple and yellow. Again, we're seeing a little deviation between these two products, and we're also seeing a lot of alignment between these two products because of the nature of the contact. Okay. So all of these are within plus or minus 5 to 7% with a different grade of cover. Okay. If you have a look at the diamond rubber, we're consistently lower with a low rolling resistance compound, around the 20% mark lower. And if we then go to the poly, we are consistently higher again. So again, 25 to 40% increase with poly for a low rolling resistance compound. Again, we are still trying to understand why this is. We believe it will come down to the viscoelastic properties of both the lagging and the cover. And hopefully we'll have some answers around this in the next 2 to 3 weeks once I've got some modeling. Okay. Okay. Just to finalize this, I thought I'd just touch on the future directions of where some of these questions will hopefully end up. Okay, so at the moment we've only tested, or we've only got comprehensive data for 4 samples that we've gone through today. There is obviously a lot more lagging products out there that we look to assess, and obviously we want to look at these under different conditions as well. So we want to test worn samples and aged samples, contaminated samples with water, iron ore, different bulk material compounds as well. And temperature dependence is going to be a critical property that we're trying to assess. Basically, the viscoelastic nature of these compounds is that the performance varies greatly if it's at minus 20 degrees or plus 40 degrees. Okay, so we're trying to come up with a plan to test at these temperatures, and again, hopefully in the not too distant future, we should have some results. Okay. The immediate criteria, I suppose, is just understanding the progression of shear and creep within the contact, because ultimately this is going to be used to define our coefficient of friction, and then ultimately we'll take that to optimize the drive systems from there. But our plan here is to replace the lagging or the belt with a rigid profile, being a bit of machined steel. And by running the same test and extracting the same data, we should be able to look at how the shear and creep progress within the contact, and then essentially remove it and calibrate it out of the results. Okay. Now, I've touched on the viscoelastic modeling. That's one of my PhD students. He's running that at the moment. He's essentially modeling the test that we're doing at the moment, and he's running an optimization process and a curve fit process to select viscoelastic parameters that provide the best fit for all of the test conditions. So this isn't a fit for a single test process. He's running a multi-parameter fit to provide the best curve fit to all test conditions. Yep. And then ultimately we want to extend this to larger scale as well, which is my final slide of this afternoon, which is this system here. This is the end goal of this research. Now, this is a grant application that we are submitting in the hope that the government will provide some funding for this research. This is a full-size representative test facility that will allow us to look at coefficients of friction, shear forces, normal forces, essentially around the arc of contact of a pulley, as well as across the across the face of the pulley. The way this system works is the best description is that it's a full-size conveyor system condensed into about 10 to 12 meters in length. Okay, so we've essentially taken the friction out of the idlers and the components in the middle of the belt conveyor, and we've pushed the two pulleys together. We're creating a T1 and T2 differential using these two drive systems here. These are big hydraulic Haglund's drives. And by opposing them initially, we can create a T1, T2 differential and then basically drive them in unison to represent that, that operating condition, okay? Now, while it's being driven, you can see just down here, these cells represent a measurement cell. Underneath each of these cells, which is underneath the lagging and in the shell of the pulley, there will be multi-axis load cells monitoring shear and transverse forces, normal forces, torsions, basically everything that we can to determine what friction is doing between the lagging and the belt. Okay, it will tell us how friction changes and how forces changes around the arc of contact. If we put on a worn belt and basically flip it, we're basically got a worn belt in contact with the drive pulley now. We will see how the shear forces and normal forces vary across the face width, and therefore how friction changes across the face width. And then ultimately all of this leads to quantifying the forces that is being seen by the pulley and the lagging itself, and also the belt and the pulley cover. Okay, so if we know what forces are being seen within this contact, we can basically better design and better select the lagging and belt compounds as well. Okay, that's a bit of a brief overview of where research is. I appreciate that hopefully it's answered some questions, but I dare say it's posed a few questions as well. It certainly has for us. The more that we dig into this topic, the deeper the hole is, we realize, and we're certainly seeing the need for this research, I suppose, and it's good to have the feedback from industry, and it's also good to see the turnout this afternoon as well. So thank you for your time this afternoon. If you do have any questions, feel free to put them in the chat, and either myself, Taryn, or Brad from Conveyor Dynamics will hopefully be able to answer them. Thanks for your time.
Thanks, Peter. Thanks for the presentation. I'll invite everyone to, if they have any question, they can just ask or write it down in the chat box. I'll ask Mariana to facilitate the questions. We have already received few questions, and I'll ask Mariana to facilitate them or direct them to relevant person.
We'll quickly go through the questions. Thank you everyone for sending them. One question I do have for you, Peter, before we start reading the questions from the participants is, we came up with a testing method with the testing rig that you showed a photo of, and we are also trying to define what friction limit is. Does that mean that the industry doesn't have this defined and there's no testing method from the industry?
There's limited information available, Marianne. It's a really good question. I'd say I'd comfortably say, without promoting this research, that this would probably be seen as best practice in industry at the moment. Until, say, the last 5 or 10 years, the need for this research has been much lower. The release of gearless drives and the exponential increase in drive capacity is what's driving this, pardon the pun. But in terms of this facility that we've got here, it would answer 80% of the questions that we'd have, looking to define the coefficient of friction limit, and hopefully in the not too distant future, how that changes with contamination, with belt wear and age, with temperature. But at the end of the day, there's always going to be a few questions that we couldn't answer on this rig without going to full size testing, which is the purpose of the large rig at the end. So we can't test in dynamic situations here. It is it's a pull test, but it still does represent a static case. The
Yeah.
ability to run in a dynamic condition will change.
Thank you. Thank you for that, Peter. There's a question. I'm going to start reading the questions from the chat. There's a question from Rajiv.
Yes, sir.
He's asking about, and maybe this one would be good if you give us your input, Brad Lawson from Conveyor Dynamics. He's asking about the relationship between the rubber hardness and the friction limits. Do you have any comments on how the hardness on the rubber, either on a rubber lagging or a rubber backed ceramic lagging, can affect the friction limit?
Hey, Mariana. Thanks for the presentation, Peter. That was excellent, by the way. Hopefully you can hear me okay?
Yep.
Excellent. So, good question. Firstly, when you have rubber belt and rubber lagging contact, definitely the durometer or hardness of the lagging and the belt that's in contact with will have an impact upon the friction and shear stress that can be developed as the slip grows from 0 to the limit. So it's something that is definitely a factor that needs to be considered. We haven't done a lot of testing with varying rubber hardnesses in the lagging to date. We've been focusing on sort of the core base lagging products, but certainly there's going to be a dependency there because of the microscopic interaction and the viscoelastic behavior of the rubbers. And I would say that the softer the durometer, I would expect that to be a higher friction developed, particularly at the lower pressures. If you're looking at a rubber-backed ceramic material where it's not in direct contact, it's a backing material, it will likely skew the friction behavior versus the shear distance or the distance of creep between the surface of the belt and the pulley itself. So I wouldn't expect it to change the maximum, but I would say it would delay the peak being reached as displacement grows. So yes, it's definitely got an impact, particularly with direct contact of belt on rubber leggings.
I hope, Rajiv, that answered, but if not, we can communicate by email and then get you in contact with Brad or Peter and get into more detail. The next question is about is from Bhaskar.
Yes, Bhaskar.
And he's asking about the friction factor recommendations from SEMA and other standards, and how our research is going to be useful to change the design of a conveyor or the rating of the belt, and how we're going to be able to combat the standards that are so conservative. I'm not sure if I read the question the right way, but that's what I'm understanding. And I think that that's a big challenge, and probably Peter is going to be the best one to answer this. But yeah, I'm not sure, or also Brad can help us with this one.
I might start, but ultimately, I think I might hand over to you, Brad. The design standards are quite conservative, as we saw, but some conveyor designers, including Brad, are looking to go one step further and look at the development of pressure and slip around the arc of contact. So in terms of a blanket approach, if you like, the design standards are quite conservative, and ultimately technology allows us to build on those, if you like, just as Brad's doing. But in terms of changing the design standards, what we're hoping to do is, if we can get a full understanding of how face pressure and slip is changing around the arc of contact, then there's a few options. One is we could look to work out an equivalent coefficient of friction that utilizes the existing Capstan equation in the standards, and of course with a factor of safety in there. But at the end of the day, with the number of lagging materials on the market at the moment, it could be best the best solution just to test an individual lagging for a given belt application. Brad, did you have anything to add to that?
Yeah, it's an interesting one. Like you explained, the standard friction factors that have been generally adopted and used by industry for conveyor drive traction design, that stood the test of time, and they've traditionally been sound and good practice. Like you've said, that once we start pushing the limits, with higher face pressures, faster belts, more power, higher shear stress being transmitted, then you start seeing a breakdown in that standard sort of friction factors, and also the conservative design, and therefore in some circumstances actually a detrimental internal effect on the lagging itself to be able to withstand those high pressures and high stresses. So I think we're not necessarily trying to set a new standard as such, or a new proxy standard, but certainly giving the industry some awareness around the challenges and limitations of those standard friction factors, so they can be informed to pursue the tools and the understanding to be able to better analyze and select lagging for a given conveyor application. And potentially, for CDI, we're pushing bigger, faster, stronger, better, but we also do assist clients with existing designs that have had shortcomings on the lagging end. The number of inquiries have been going up exponentially in that regard. Certainly with this type of understanding, it allows us to determine the root cause and rectify these problems, but also for new conveyor designs, we're able to optimally select the lagging and drive pulley arrangement to be able to both utilize the knowledge in the friction and how the shear stress is developed during rapid pulley, but also able to reduce the costs of the system, the total cost, which then makes us more competitive in a competitive tendering and bidding market with our clients.
And that probably leads onto the next question from Taylor Jobson, asking, is there any way we can quantify the relationship of the way the conveyor is operating and check it against its friction limits to get an idea on the performance? And this is actually the way we are using this information from the testing that we're doing. We're using these friction limits that we're getting from this testing to calibrate the software that we're using to understand potential slip between the belts and the drives. And I'm not sure if that's what you were asking, Taylor, but yes, the software that we are developing together with Conveyor Dynamics that we're using these testing results for has the ability to analyze the likelihood of slippage on the drive pulleys between the lagging and the belt. So yes, there are methods to calculate that, and we can definitely share that. We will probably engage with you later to show you how that's done. The next question, let me read as a previous photograph. I see, Rajiv Kumar, he's asking about the horizontal grooves on the rubber lagging, or what all the laggings that were shown. And he's saying that normally on rubber lagging, he doesn't see those horizontal grooves. Here, well, we know that we have the full diamond one with no horizontal grooves, which normally has to do with the hand grooving, and the molded lagging that is done in strips. To be able to fit the last strips on a pulley has the horizontal grooves. What is the advantage of having those horizontal grooves? It's more for an application matter. It has nothing to do with performance. We know that the grooving does affect the friction limit because it affects the flexibility of the lagging, but there's no direct relationship, and no, the horizontal grooves are there for a specific reason. It has to do more with an application, practical application of the lagging onto the pulley. That's when the lagging is applied on strips. Then Gary James is asking, can the pressure range be increased to 1.7 megapascals in the testing?
Yeah, it can, Gary. So what we'd do there is we'd simply reduce the contact area. Typically, we make the belt a little bit thinner, and so we still maintain the full 5 segments of lagging in length. But yeah, we should be able to get to 1.7 MPa.
Yeah, that's good. Look, just sometimes at the entry on some pulleys, on the T1 side, you can get quite high pressures, and if there's a transition there and so forth, you can actually have these, and typically 1.7 is sort of allowed by the old Goodyear sort of numbers as well. You can go up to those sort of numbers, but you're really achieving not much friction factor at that pressure. That's quite low. But it'd be nice to see the graphs that at that sort of range if you've got them.
Yeah, definitely. We don't have data at the moment. We did some initial testing at 1.2, and essentially the curves continued, I suppose. But I can definitely look into the possibility of testing up to 1.7.
1.2 is the old benchmark that Bando and many others used to use, even Goodyear at one stage. But look, there are many pulleys that are with much higher pressures than that. Anyway, that's just an interesting thing that I'd be keen on seeing if you've got that sort of data.
Yeah, absolutely.
I can just add something as well, Gary. What I've noticed in the testing is that as the normal pressure increases, the peak shear stress that can be developed basically plateaus. So effectively, you have a friction factor that starts to taper off because as the normal pressures are increasing, the shear stress or the friction stress that's developed is maintained as a constant somewhat. So you don't see much change in the peak shear stress that can be developed as you get over into those higher range pressures.
Yeah, that's correct. And the friction factor crashes really, but
yes.
it's just something if you're analysing it, that's the sort of data you're dealing with. And even though it's not ideal, that's sometimes that's what you've got to deal with.
Now, certainly in these big these direct gearless drives now, they're pushing pressures up into those ranges.
Yeah,
for sure.
That's right.
That's where the application
Thank
is.
you, Gary and Brad. There's another question from Josh Wilkie from Rio Tinto. He's asking about friction definitions. Is there a way we could define friction for different operating conditions of the pulley, like the start, run, braking, or loaded conditions? Is this something we should consider when we are defining friction? Peter, I hand this over to you.
It's a good question, Josh. I wouldn't expect there to be any difference in definition between, say, a brake application or a drive application. Ultimately, the shear is just imposed in the opposite direction for braking compared to driving. In terms of loaded, unloaded, etc. Again, I think that a single definition would hold true for all of them. What that definition is still a bit of the grey area, and that kind of feeds into Gary's question afterwards, comparison with Flexco data. The definition of friction in the Flexco papers is that they take a coefficient of friction at a given displacement or a given shear, if you like, of about 1/4 inch between the belt and the pulley. It's certainly a definition that we're looking at the moment, but ultimately we're presenting three coefficients, being a peak, a steady state, and a Flexco equivalent at 1/4 inch, and basically assessing from there. So as we saw in the first, I can't remember which slide it was, sorry, back towards the start, the rate of shear of the laggings changes. And if we take a fixed displacement, we'll end up with a conservative approach or a realistic approach, depending on the thickness and the viscoelastic properties of the material. So it's certainly a definition that we need to specify. But in terms of changes with application, I wouldn't expect it to change.
This is a hangover from decades of standards, BHP and Rio Tinto and so forth, having pushing the friction factor a bit harder on startup and so forth. They used to allow, say, for ceramic was 0.45 for startup, and for running might be 0.35 or something. It's just there's definitions within their standards. That's what they used to allow. So safety, basically the safety margin on startup would be reduced, you know, by either using a 0.45 for startup or a 0.435 for running for ceramic. So it's sort of something that's lingering in the old specifications that have been used for decades.
Okay, I misinterpreted that question. Thanks, Gary.
Yeah, I think that's what it's. Perhaps the person who asked the question might be able to explain, but that's what I think it's about. And but look, as you do more research, some of those definitions will fall away, I think. You know, it's just as important not to have slip at startup as running, so or braking. So, you know, and as you get better knowledge, we can redefine these specifications. The other thing you've got to drag along board is really all the belting suppliers as well. And you've got to drag along DIN and ISO and SEMA. I mean, you might choose a different standard here, but a lot of these people will be reluctant to follow you quickly. I mean, so there'll be a point where you'll have to satisfy a number of conflicting bodies, belt manufacturer or a SEMA or whatever. But anyway, you need to hammer these things, get better knowledge, and then you can show where things can be changed.
I think the one thing that I'd add there, Gary, if we're looking at a start compared to normal running, would probably be the temperature dependence of these materials. If we're looking at a cold start versus a normal running, you're absolutely right. The need to minimize slip is quite similar in both those applications, but the temperature of the lagging is going to differ in both those applications. So that's certainly something that we're hoping to look at down the track. And yeah. We've run some very preliminary temperature testing. We haven't got an environmental chamber as of yet, but our thermal camera, putting it on the belt as it comes out of the frictional contact, there's a noticeable increase in temperature of the belt and the lagging as well in the contact, and all of that comes into play.
Thank you, Gary and Peter. There's a question also about how there's other research done previously on friction between lagging and belt, and the question is about how we compared our research results to other papers that have been published. It is part of Jason's PhD as well.
So Jason, I'm not sure if Jason's on the call actually. Jason's my PhD student who's a whiz in this area, to put it mildly. He has investigated every prior work, if you like, and you're absolutely right. There has been some work in this field. Flexco that Gary spoke about has done some similar work on their products as well. In terms of a generic approach, we're not aware of a sound approach at this scale, if you like. The majority of the test data that we've seen has been done at lower loads, lower speeds, and different products as well. Some of them have different applications. So there's some information that we can utilize from previous work, but the majority of our approach is much larger than anything that's been done previously.
My question related to can you just repeat the Flexco work? For example, you might have different philosophy and you might choose different creep speeds and all sorts of things for different reasons.
Yep.
but I'd be keen to see whether you can even repeat the work that was done by De Vries. And then you might say, well, we're choosing not to do that. We're going to choose a different creep speed or something, or a different displacement, or different conditioning and so forth. Anyway, look, I think it'd be worth seeing, can you even on the same graph put the De Vries work, and how does it look the same? I mean, on your rig.
Yeah, definitely. The rig certainly took some inspiration from De Vries. There's no discounting that. The materials are different, obviously. The 1/4 inch that we spoke about is De Vries work, but the data that we've got basically allows us to dig a little bit deeper into the results. The data that I also presented at 2 inches per minute, that is the test velocity that De Vries utilizes in his test, which is where we took it as our baseline. Brad and Taryn are looking at, I suppose, optimizing that creep velocity, and perhaps Brad, you can talk a little bit more, but it certainly does vary with application.
So your graphs look different to De Vries's graphs, or they're in the same ballpark, or they're just not even on the chart, or?
We see similarities, certainly consistencies with behavior. I wouldn't say that there was any differences that would be concerned about, seeing as we're testing different materials. But yeah, we certainly do see similarities.
I think that the displacement that we used was larger, and we could see the full curve, while De Vries stopped the testing early, and you couldn't see. Is that right?
Yeah, that's right.
But
Stop the displacement at 6.35 millimeter, and we are doing it for 60 millimeter.
So we get the full shape of the curve. And that's one of the differences. But the part that we are, if we compare the same displacement to the same displacement, it's similar.
Right.
There's a question from Joachim regarding the lagging select software tool that Tarun mentioned when the presentation started. As Tarun said, this webinar, this research on friction is a small part of a larger research program that Elastotec, the uni, and Conveyor Dynamics are working on, and it's only a small part of a bigger project. The project involves other aspects like understanding the fatigue of the lagging. So there's going to be subsequent webinars explaining different parts of the analysis that we're doing. And yes, all of this information that we're getting from this testing and this research is being used to calibrate this software that Conveyor Dynamics and Elastotec developed together. And Tarun can give you a brief explanation. Maybe later he can contact you directly and explain you how the software works and how to get access to it. But yes, this is under development. We have the offline version running. We've been using it for 2 years or 1.5 years. Yes. Now the online version is in progress. We have the temporary version, the preliminary version already working. We're testing it. And then the idea is that we use this with our partners to improve the lagging selection and the lagging capability for each application. But Tarun will engage with you, Joaquin, on that.
Sure, Joaquin, yeah.
From my side, Peter, and maybe Brad as well, I'd like to find, there's a couple more questions that we can address privately, but from my side is, being a lagging specialist, pulley manufacturers or conveyor designers come to us and ask us, what's the coefficient of friction of each of your laggings? They say, well, you have the 80% ceramic lagging, 12 mil thick. What can I use up as a coefficient of friction limit? What do I answer to that?
Yes, it's a tricky one because now we know too much. So basically it's extremely difficult to define a standard coefficient of friction, I believe. Now that we have the tool and the knowledge around the friction, which affects how the shear stress and the traction is developed around the wrap of the pulley, and how the lagging is able to withstand that, then we can make an informed decision about what the best lagging fee application is. I don't think there's a practical way where we could rewrite the book on what lagging friction is going to be developed for a given product, because it's too dependent, in all honesty, in the application and the conditions in which it's operating under. So I think that's
the title of the presentation, friction is not friction.
oils and oils. Yeah, that's correct. And you know, the Euler, you know, the standard industry friction values that have been used, the reason for that is because they're conservative values. They can be applied relatively safely, certainly from a macro slip, you know, bulk slip condition management. That's one thing as well, Gary, you're talking about previously, you know, with your starting friction factors, you know, being higher than your running friction factors. I believe that's because during starting, you're looking at bulk slip really as the criteria to address. But during the running condition, that's when you know, traditionally a lower coefficient friction has been used, and the reason for that being that during running conditions, which it's operating at, you know, 95 plus 98 time. If you do have localized slip occurring because of the frictional contact between the belt and lagging, then that introduces a wear aspect, and wear is time, you know, cycles. It's a wear criteria rather than a purely bulk slip criteria as friction factors go.
Thank you, Brad, for that. There's other questions that we will reply privately. I think we're going to leave it here for now, so we don't drag it too long. But thank you everyone for engaging, for joining, and you'll get a link with a recording of this. And if you want to share these with anyone that you think would be interested, you're welcome to do so. And you can contact us for any extra information as well. And we'll be doing subsequent webinars with new results and different areas of research. So we'll be in touch.
Thank you, everybody. Thanks for joining.
Thank you, Peter. Thank you, Brad.
Thank you, everyone.
Yeah, thank you all. That's excellent. Cheers, Gary.
Thanks.